Okay, let's start with the basics. What asterisk is asterisk data science? Simply put, it's about turning raw information into useful knowledge. Think of it as a blend of statistics, computer science, and even business expertise. Data scientists dive into datasets, clean them up, figure out what they mean, and then use those insights to help organizations make smarter choices. It's not just about doing the math, it's really about understanding the story the data is telling. Okay, let's talk about what data scientists actually do. It's more than just coding. They start by collecting data from all sorts of places, databases, websites, even scraping information. Then they need to make sure that data is clean and accurate. Next, they dive in with exploratory data analysis, essentially asking what's going on here using charts and stats. They then engineer new features, which are basically creating better ingredients for their models. After that comes the exciting part, building predictive models using tools like Python. But it doesn't stop there. They constantly evaluate these models to make sure they're working properly, and finally, they have to communicate those findings in a way everyone can understand, turning complex data into valuable business insights. Okay, let's talk about how data scientists actually do their work. It's not just magic. There's a really useful process they follow called the data science lifecycle. It starts with understanding what you're trying to achieve, finding the business problem, and making sure everyone is on the same page. Then, they gather the necessary data from various sources, checking that it's good quality. Next comes exploring the data, cleaning it up, transforming it, and looking for interesting patterns. After that, they build models using those patterns, testing how well they work. Finally, they deploy the model into a real-world situation and keep an eye on it to make sure it's still accurate over time. It's like a continuous cycle of learning and improvement. Okay, let's talk about exploratory data analysis, or EDA. Think of it as the first step in any data science project, a really important one. It's all about getting to know your data intimately. We start by cleaning up any messy bits, like missing information or strange values. Then, we look at each variable on its own, using things like histograms and box plots. Finally, we dig into how the variables relate to each other. Scatter plots and correlation matrices are our friends here. It's a process of discovery that helps us understand what's really going on in our data. Okay, let's talk about cleaning and prepping our data. This is really important. Think of your raw data as a bit of a mess. It'll almost certainly have missing values, weird outliers, or maybe even some duplicated entries. The good news is there are tools to tackle these issues. We're going to look at how we handle missing information, things like replacing with the average or removing those raws altogether. Then we'll talk about getting rid of those extreme values that can throw off our models and making sure everything is in the right format, like turning a text field into a number. Standardization and normalization are also key. They help algorithms work better when features are on different scales. Okay, so let's talk about feature engineering. It's a really important step in building effective data models. Think of it like this. Your raw data is like a pile of ingredients, and your model needs specific recipes to make something delicious. Feature engineering is the process of transforming those ingredients into those perfect recipes. It's often more impactful than simply picking a different algorithm altogether. We'll look at why it matters, because raw data rarely holds all the clues you need. We'll cover techniques like scaling your features so they are on the same playing field, encoding categorical variables like turning text into numbers, creating polynomial features to capture nonlinear relationships, and even combining existing features. Domain knowledge is absolutely key here. Understanding what those features mean will help you create the most effective ones. Okay, let's talk about outliers. They're those data points that just don't fit the pattern. They are way off on their own. Detecting them is the first step because they can really mess up your models and analyses. We have a bunch of tools to spot them, from simple stats like z-scores and IQR to visual methods like box plots, which show you those extreme values right away. Clustering algorithms like dbScan are also great for finding points that seem isolated. Once we've found an outlier, it's important to decide what to do about it. You could remove it if it's clearly a mistake, or try transforming your data with something like a log transformation to reduce its influence. Winsorization is another option. Basically, you replace the really extreme values with more reasonable ones. Okay, so when we have missing data in our datasets, it's really important to handle it thoughtfully. There are a bunch of techniques you can use. Some simple ones like mean or median imputation, just replacing the missing values with the average or middle value of that column. That's easy but can sometimes skew your results. Then there's mode imputation for categorical data, which picks the most common category. For more complex situations, we have KNN imputation, where we look at similar rows to guess what the missing value should be. And regression imputation uses a model to predict those values based on other variables. Finally, multiple imputation is a really powerful technique that creates several datasets with estimated values, giving you a better sense of uncertainty. Okay, let's talk about transforming and scaling your data. These are really important steps before you dive into building a model. Think of it like making sure everyone is playing by the same rules. Many algorithms struggle when features have wildly different scales, so we need to bring them into line. We often do this by scaling features to a specific range, like between 0 and 1, or standardizing them so they all have a mean of 0 and similar spread. And sometimes we apply transformations like log transforms to handle skewed data distributions. It's about making your data more suitable for the algorithms you're using. Okay, so when we're building a data science model, it's not enough just to throw in all the available data. We need to be smart about which features or variables we include. There are three main categories of feature selection techniques: filter methods, wrapper methods, and embedded methods. Filter methods use statistical tests like correlation to score each feature independently of the model, which is quick but might miss how features work together. Wrapper methods involve training a model with different combinations of features to see what works best. It's slower, but often more accurate. And then there are embedded methods, where feature selection happens naturally as part of the model building process itself. It's really important to remember that you should always check your choices by using cross-validation to make sure you aren't just creating a model that performs great on the training data but poorly when it encounters new information. Okay, let's talk about supervised learning. It's a really important part of what we do as data scientists. Basically, we teach our algorithms by showing them examples where we already know the answer. So, if we're trying to predict house prices, we show the algorithm lots of houses with their actual prices. Then it learns how to associate features like size and location with those prices. We can broadly divide supervised learning into two categories: regression, which is used for predicting continuous values like temperature or sales figures, and classification, where we're trying to predict a category like whether an email is spam or not. There are a bunch of powerful algorithms we can use, from simple linear regression all the way up to more complex techniques like random forests. The best algorithm depends on what kind of data you have and what you're ultimately trying to achieve. Let's talk about unsupervised learning. It's like giving a computer a bunch of data without telling it what to look for. Instead, it tries to find interesting groupings or patterns all by itself. We have some key players here. K-means is really good at finding clusters based on similarity. Hierarchical clustering builds a family tree of clusters. And dbScan can spot dense areas and identify anything that doesn't fit in. Those are often considered outliers. The best algorithm for your situation will depend on the specific data you're working with, so it's important to experiment. Okay, let's talk about reinforcement learning. It's basically teaching a computer to make decisions like you would teach a dog. The core idea is that an agent learns through trial and error, receiving rewards for good actions and penalties for bad ones, kind of like a game with points. We have the agent, which makes the choices, the environment it operates in, the current situation represented as a state, what the agent does in action, and finally, a reward that tells it if it did something right or wrong. It's a really powerful technique for solving complex problems where you don't have labeled data, just an interaction with the world. Alright, let's dive into classification algorithms, essentially how we teach a computer to predict which category something belongs to. We've got some really powerful tools at our disposal. First up, logistic regression is a great starting point for binary problems, like deciding if an email is spam or not. Then there's support vector machines, which are super effective when you're dealing with lots of features. Decision trees help us visualize the decision-making process. Random forests build on that by combining multiple trees to be more accurate. And finally, gradient boosting techniques like XGBoost are incredibly powerful for getting top-notch results. Okay, let's talk about regression algorithms. These are super important for predicting things like sales numbers or house prices. We'll start with the basics. Linear regression, it just finds the best straight line to fit our data. Then we'll move on to ridge regression, which helps us avoid overfitting by shrinking some of those coefficients towards zero. Next up is lasso regression, which can actually remove unimportant features from our model entirely. And finally, ElasticNet combines these ideas for a really flexible approach. Let's dive into clustering algorithms. These techniques help us find hidden groups of similar data points without needing to label them beforehand. We'll look at k-means, which tries to create distinct clusters based on average positions. dbScan, that's great for finding shapes and dealing with outliers because it focuses on density. And finally, hierarchical clustering, where we build a hierarchy of clusters, imagine starting with each data point as its own cluster and slowly merging them together. Each algorithm has its strengths and weaknesses depending on your specific data set and goals. Do you have any questions about these approaches? Let's talk about how we deal with tons of data like a spreadsheet packed with hundreds of columns. It can be really tricky to work with, but that's where dimensionality reduction comes in. Essentially, it's a way to simplify the data while still keeping the important information. PCA is a classic method. It looks for the main axes of variation within your data and focuses on those. TSNE is amazing for visualizing clusters, especially when you have complex datasets. And UAP is gaining popularity because it tends to work really well with larger amounts of data and can show how things relate to each other in a more meaningful way. Okay, so building a good machine learning model is only half the battle. We need to know if it's actually good at what it's doing. We use these metrics to evaluate how well our models are performing. Accuracy just gives us the overall percentage of correct predictions, but that can be tricky with uneven datasets. Precision tells us about false positives. Recall focuses on missing actual positive cases. Think about identifying fraudulent transactions. The phone score is a nice balance between them. And finally, ROCAUC is a really powerful tool for understanding how well our model separates the different classes, giving us a good overall picture of its performance. Okay, let's talk about cross-validation. It's a really important tool for data scientists. Basically, it helps us figure out if our model is going to perform well when we apply it to new, unseen data. We don't just rely on the training set, which can give us a biased view. Instead, we split our data into several folds. One common method is k-fold cross-validation. You divide your data set into k pieces and train and test the model k times, each time using a different fold as the test set. Stratified k-fold is similar, but make sure each fold has roughly the same proportion of classes if you have an imbalanced data set. And then there's leave one out cross-validation. It's really thorough because every single data point gets used for testing at least once. Choosing which method to use depends on how much data we're working with, but generally, cross-validation gives us a much more reliable estimate of our model's true performance. Okay, let's talk about getting your machine learning models to really shine. We often have to adjust settings called hyperparameters. These aren't part of the data itself, but they control how the model learns. There are a few different strategies we can use to find the best hyperparameter values. Grid search is like systematically trying out every possible combination within a set range. It's simple, but can be slow if you have lots of options. Random search just randomly tries things out. Surprisingly, this often works really well. And then there's Bayesian optimization. It's a more intelligent approach that uses probabilities to guide its search, learning from previous attempts and focusing on the most promising areas. Okay, let's talk about how we can predict what will happen in the future using time series data. We're going to look at some really useful models: Zerma, Sorama, Prophet, and LSTM. ARMA is a classic statistical approach that digs into how values relate to each other over time. Then there's SARMA, which adds seasonal patterns on top of that. Profit, created by Facebook, is fantastic for business forecasts because it's really good at handling things like holidays and trends changing unexpectedly. Finally, we have LSEM, a more advanced type of neural network that can remember longer-term relationships in the data. Picking the best model depends on your specific situation, how you've collected the data, and what you are trying to predict. Okay, let's dive into natural language processing. This slide focuses on getting our text ready for analysis. The first step is preprocessing, basically cleaning up the data by removing things like punctuation and converting everything to lowercase. Then we get rid of common words that don't add much value, and finally reduce words to their basic form using stemming or lemmatization. Next up is tokenization, which is all about splitting our text into individual units, typically words. See this simple Python code, it shows how easy it is to break a sentence down into tokens. Okay, let's talk about uncovering hidden themes in text data. That's what topic modeling is all about. We have two main approaches we'll explore, LDA and NMF. Topic modeling essentially finds the underlying topics within a set of documents without us having to label them ourselves. LDA treats each document as a blend of different topics, while NMF uses a clever mathematical technique to break down the data into its component parts. LDA is more probabilistic, like a detective piecing together clues, whereas NMF uses matrix factorization to find those hidden connections. Both are really useful tools for understanding large amounts of text. Okay, so let's talk about text classification and sentiment analysis. These are really valuable techniques for data scientists. Basically, they're ways to get computers to understand what we're writing. It starts with cleaning up the text, getting rid of things like punctuation and turning everything lowercase. Then, we need to turn that text into numbers that a computer can actually work with, using methods like bag of words or more advanced techniques like word embeddings. Once we have those numbers, we train a machine learning model, something like Naive Bayes, on some labeled data. Finally, the model can predict what category the new text belongs to, or what its overall sentiment is, whether it's positive, negative, or neutral. Okay, let's dive into deep learning. It's essentially a powerful tool within the broader field of machine learning. Think of it as teaching computers to learn in a way that mirrors how our brains do, using layers of interconnected nodes. These networks analyze data and make predictions based on what they learn. We'll talk about the basics like neural networks, different types of layers, and some common architectures you'll hear about often, such as CNN for images and RNN for things like text or time series. Okay, let's dive into artificial neural networks, or ANNs. Think of them as digital brains. They are a really important tool for data scientists because they can handle incredibly complex problems. Basically, an ANN is made up of layers of interconnected nodes, kind of like neurons in your brain. The first layer takes in the raw data, then hidden layers do all the heavy lifting with calculations, and finally, the last layer gives you the answer. The magic happens when these connections between the nodes have weights that are constantly adjusted during a process called backpropagation. It's like learning from mistakes. And they use something called activation functions to make those adjustments effective. It sounds complicated, but essentially ANN allow computers to learn patterns and relationships in data that would be impossible to spot with traditional methods. Okay, let's talk about convolutional neural networks, or CNNs. These are a really powerful tool when we're dealing with images. Think of it like this: instead of just feeding raw pixels into a network, CNN use something called convolutional layers. These layers essentially slide small filters across the image to find patterns like edges and textures. Then, pooling layers help reduce the size of the data while still retaining important information. Finally, fully connected layers take all those learned features and make a prediction, whether it's classifying an image or something else entirely. The cool thing about CNN is they automatically figure out what's important in an image. You don't need to tell them exactly what to look for. Okay, let's talk about recurrent neural networks, or RNNs. These are really useful for when you're dealing with things that come in a sequence, like sentences or time series data. Think of it like this: regular neural networks just look at one piece of information at a time. But an RNN remembers what came before it, has memory. This makes them fantastic for tasks like understanding language, predicting trends over time, and even converting speech into text. They have a special hidden state that carries information forward, and they use feedback loops to keep track of the past. Now, there can be some challenges with training RNN, particularly things called vanishing or exploding gradients, but techniques like LSTMs and GRU help us overcome those issues. Okay, so let's talk about transfer learning. Imagine you're trying to build a model to classify different types of dogs, but you only have a small dataset. That can be tough. Transfer learning is a really clever technique that lets us shortcut this process. Basically, we start with a model that's already been trained on something huge, like millions of images of everyday objects. Then, instead of building a model from scratch, we use the knowledge it's already gained to help us learn our specific task more quickly and effectively, often with much less data. It's like giving your new model a really solid head start. Okay, so let's talk about object detection and image classification. They're both really important parts of computer vision. Image classification is basically figuring out what's in a picture, like saying this is a cat or this is a dog. Object detection takes it a bit further. Not only does it tell us what's there, but it also tells us where it is by drawing boxes around each object. These techniques are used everywhere from self-driving cars to security systems and even in retail to count products on shelves. Pretty cool, right? Okay, let's talk about data visualization. As data scientists, we need to be able to clearly communicate what our data is telling us. There are a bunch of fantastic tools available to help with that. We've got Matplotlib, a really flexible Python library for creating all sorts of charts and graphs. Then there's Seaborn, which builds on Matplotlib and makes it super easy to create those common statistical plots you see all the time. Plotly is great if you need interactive visualizations or want to embed your charts in web applications. Tableau and Power BI are powerful business intelligence tools that are fantastic for building dashboards and exploring data, especially if you're working with a large organization. They can be really helpful. Ultimately, choosing the right tool depends on what you're trying to achieve. Let's talk about how we handle those truly massive datasets. First up, Hadoop. Think of it as the foundation for storing all that information across a cluster of computers. It uses HDFS, which is like a super distributed file system, and MapReduce, a process to divide work into pieces and do it in parallel. Now, Spark comes along to speed things up dramatically. Instead of relying on slower methods, Spark can often process data directly in memory, making queries much quicker. And finally, we have Hive. Essentially, it's SQL for Hadoop. It lets you query your data using familiar commands, even if the data is stored in a really complex way. Okay, so today we're talking about a really important part of the data scientist workflow: data warehousing and SQL. Basically, a data warehouse is like a giant archive designed specifically for analyzing data. It's not where your website transactions live. We need to understand how it differs from regular databases, which handle real-time actions. Then we'll explore some common database design patterns called star and snowflake schemas, and the all-important ETL process: extract, transform, load, which gets your raw data ready for analysis. And of course, SQL is our go-to tool for actually working with this data. It allows us to query, summarize, and combine information in powerful ways. Okay, let's talk about NoSQL databases. These are a different beast compared to the traditional relational databases we often hear about. Instead of sticking to a rigid table structure, they offer much more flexibility. MongoDB stores data in JSON-like documents, think super organized collections of information. Then there's Cassandra, which is built for massive scale and reliability, making it great when you need your system to keep running even if parts go down. Essentially, choosing the right database depends on what kind of data you're dealing with and how important speed and availability are. Okay, let's talk about where data scientists get their information. Sometimes it's not stored nicely in a database, so they use tools like Data API and web scraping. Data API are basically digital requests you ask for specific data, and the website gives it to you in an organized way. It's similar to ordering from a menu. Web scraping is when we dig directly out of websites to find information. We've got some great tools like Beautiful Soup, which is really easy to learn, Scrapy, which is powerful for bigger jobs, and Selenium that helps us automate browsers if the website needs them to load first. But remember, always check the rules of the website before you start scraping. Okay, so let's talk about how we get our data from where it is to where it needs to be, creating efficient and reliable data pipelines. A data pipeline is basically a series of steps that automatically move and transform data. Imagine an assembly line for your information. Automating these processes saves us tons of time and effort, makes sure everything's done consistently, and allows us to handle really large amounts of data without any problems. Two popular tools we often use are Apache Airflow. It's a powerful platform that lets you programmatically design and manage complex workflows, and Luigi, which is a more lightweight Python module perfect for simpler transformations. Essentially, they both help us build robust and scalable data flows. Let's talk about how cloud platforms can really level up your data science game. We have three major players: Amazon Web Services, Google Cloud Platform, and Microsoft Azure. Each offers a comprehensive suite of tools. Think massive storage like S3 or cloud storage, powerful computing resources like EC2 or Compute Engine, and dedicated machine learning platforms like SageMaker, Vertex AI, and Machine Learning Studio. When it comes to comparing them, they all offer similar core components, so the best choice often depends on your existing tech stack and specific project needs. Okay, so we've built our amazing model. But it's not really useful unless someone can actually use it. That's where deployment comes in. We need to get our model out into the world. There are a few popular options for deploying models, and today we're focusing on four key tools: Flask, FastAPI, Docker, and Streamlit. Flask is a classic Python web framework, super flexible but can require more setup. FastAPI is a newer alternative that's known for being really fast and easy to use, especially when building API. Docker lets us package our entire application and its dependencies into a single container, making it incredibly portable and consistent across different environments. And finally, Streamlit allows us to quickly build web apps around our models, great for demos and sharing. We'll dive deeper into Docker and Streamlit in the next slide. They're key to getting your model live. Okay, so you've built a fantastic ML model, congratulations. But getting it into production can be tricky. Think of it like this: you don't want one giant, complex application that's hard to manage and scale. That's where containerization and microservices come in. Containerization, using tools like Docker, packages everything your model needs: the code, the libraries, the dependencies into a self-contained unit. This means your model will run consistently whether it's on your laptop or in the cloud. And then we break that up further by using microservices. Imagine splitting your application into smaller pieces, each doing one thing really well. For example, you might have a service for processing data, another for making predictions, and yet another for storing results. Kubernetes is like the conductor of this whole orchestra. It makes sure everything runs smoothly, handles failures gracefully, and scales as needed. Okay, let's talk about keeping your models running smoothly long after they're deployed. Model monitoring isn't just an afterthought, it's a critical part of the data science lifecycle. We need to track key performance indicators like accuracy and precision, but it's even more important to watch for changes in the data itself, because that's often what causes problems. Data drift happens when the input data shifts, and concept drift means the relationship between inputs and outputs is changing. Finally, we want to ensure our models are fair and don't introduce or amplify biases. To manage this, we set up automated alerts when things start to go wrong, build pipelines to automatically retrain with new data, and always keep track of different model versions so we can quickly roll back if necessary. Let's talk about A/B testing. It's a really powerful tool for data scientists. Basically, it's like running a controlled experiment to see which version of something performs better. Think of it as comparing two versions of a website or app, randomly assigning users to each one and tracking how they behave. We start with a clear question, identify the metrics we want to measure like click-through rates or conversion rates, then carefully monitor the results to see if one version truly outperforms the other. It's all about making data-driven decisions to optimize your product or service. Okay, let's dive into how statistics plays a huge role in data science. First up are descriptive stats. Think of them as your data's personality report. We use things like the mean, median, and more to understand where the data is clustered and how spread out it is. And visuals like histograms help us see those patterns too. Next, we move into inferential statistics. This is about using a small piece of information, a sample, to make educated guesses about a larger group. Confidence intervals and correlations are key here. Finally, let's talk about hypothesis testing. This is the process of formally checking if your data supports an idea you have. It involves setting up null and alternative hypotheses, and then figuring out what probability we'd need for our results to be considered statistically significant. Okay, let's talk about probability. It's a really important foundation for anyone wanting to become a data scientist. It might sound abstract, but essentially, it's all about figuring out how likely something is to happen. We start with defining the possible outcomes, that's your sample space, and then focus on specific events you're interested in. There are some basic rules like adding probabilities when considering multiple events, but don't forget to subtract for overlap. Bayes' theorem is a particularly powerful tool. It helps us update our understanding of things as we get new information. And the beauty of it is that probability isn't just theoretical, it directly informs how we build models and interpret results in data science. Okay, let's talk about Bayesian inference. Think of it like this: you start with an initial guess, your prior probability about something. Then, as you collect data, you use that data to update your guess, creating a new, more informed belief, the posterior probability. The Bayes' theorem is the equation that describes exactly how we do this. It combines our prior knowledge with the likelihood of the observed data and gives us the updated probability. Okay, let's talk about why linear algebra is so important in data science. It might seem a little abstract at first, but trust me, it's really powerful. Essentially, we represent our data, those individual points you see in a scatter plot, as vectors, which are like arrows with direction and magnitude. And the relationships between those data points. Those get described by matrices. Dot products, eigenvalues, eigenvectors. These concepts help us understand how similar things are, identify key patterns, and even reduce the amount of information we need to work with, making analysis much easier. It's all about finding those hidden connections in your data. Okay, let's talk about how calculus plays a big role in getting our data science models just right. Specifically, we're diving into optimization. Think of it like this: we want to find the best setting, the values that make our model perform as well as possible. Gradient descent is a super common technique here. It's basically an algorithm that repeatedly takes small steps downhill, guided by the gradient, which tells us the direction of steepest descent. When we have constraints, like a limited budget or some other limit, we use Lagrange multipliers to help us find the best solution while respecting those boundaries. And finally, second derivatives known as the Hessian matrix tell us whether we've actually found a true minimum, maximum, or something in between. Okay, so we're talking about getting our machine learning models to perform well, not just in the training data, but in the real world. Optimization is a big part of that. We'll look at how we adjust things like the learning rate and how many trees are in a decision forest. We also need to be smart about which features we're using and consider techniques like regularization to prevent our models from becoming too complex, and different algorithms for finding the best parameters. Okay, let's talk about gradient descent. It's a really important algorithm that data scientists use constantly to train their models, basically to make them learn. Think of it like finding the lowest point in a valley. Gradient descent is a method that tells your model where to take its next step to get closer and closer to that bottom. We have different versions too. Batch gradient descent uses all the data at once, which is reliable but slow with huge datasets. Then there's stochastic gradient descent. It takes just one random sample per step, making it fast but a bit noisy. And finally, mini-batch gradient descent finds a happy medium between the two. Okay, let's talk about regularization, a really important concept for building robust data science models. Basically, it's a way to stop your model from memorizing the training data instead of learning general patterns. When you have lots of features or a complicated model, it can easily overfit, meaning it performs great on what it's seen before but terribly on new data. Regularization adds a penalty for complexity, so the model has to find simpler, more generalized solutions. We've got a few different techniques like Learn, L2, and ElasticNet, each with its own strengths in helping you avoid overfitting and build models that actually generalize well. Okay, let's talk about ensemble learning. It's like getting multiple experts together to tackle a problem. We often want our models to be more reliable and accurate, and ensembles are a fantastic way to do that. First up is bagging. Think of it as creating many slightly different versions of your model by training them on random chunks of your data. Then there's boosting, which builds upon its predecessors, correcting mistakes each time. Finally, we have stacking, where you train multiple models and then a meta-learner combines their predictions for the best result. It's all about harnessing the power of many. Let's talk about spotting those unusual data points anomalies. As a data scientist, you'll often need to identify these outliers because they can signal everything from fraud to equipment problems. There are several ways to tackle this. We can use simple statistical methods like Z-scores or the IQR, which look for deviations from what's normal. Then there's machine learning techniques like isolation forests and LOF that learn how data is supposed to behave and flag anything that doesn't fit in. And sometimes, we can even rely on rules based on our understanding of the data itself. The key is choosing the right approach depending on your specific situation. Okay, let's talk about collaborative filtering, a really common way to build recommendation systems. Basically, it's all about figuring out what someone might like based on what people who are similar to them already enjoy. There are two main ways this can work: user-based filtering, where we look for users with similar tastes and see what they liked, or item-based filtering, which finds items that tend to be purchased or rated together. The core idea is simple: if someone you like bought something, you might too. Okay, let's talk about content-based filtering. It's a really clever way to make recommendations. Basically, if you love something, say, an action movie starring Tom Cruise, this technique figures out what ***** is similar based on the movie's features like its genre, actors, and even the plot details. It's all about matching content that users have previously liked, creating a personalized experience. Okay, so we've built these awesome recommender systems, but how do we know if they are actually making good suggestions? Well, there are several key metrics we use. Let's start with precision at K, which tells us what percentage of the top recommendations were actually relevant to the user. Then there's recall at K, measuring what proportion of *** the relevant items the system managed to recommend in its top choices. NDCG is a bit more sophisticated. It looks at how well the system ranked the relevant items. Higher ranked relevant items are worth more. And finally, MAPBAT's mean average precision, which gives us an overall score for performance across all our users. It's important to remember that the best metric depends on what you're trying to achieve with your recommender system. Okay, let's talk about explainable AI, or SAI. Essentially, we're building these incredible machine learning models that make predictions, often really accurate ones. But sometimes, they are like black boxes. It's hard to figure out why they made a specific decision. That's where XAI comes in. It's all about making those models more transparent and understandable. Why is this important? Well, people need to trust the model. We want to be able to find and fix any biases or errors, and increasingly, regulations like GDPR require us to explain how our decisions are made. There are a few key techniques out there. LIME helps us understand individual predictions by creating local approximations of the model. SHAP uses game theory to figure out which features were most influential, and if your base model is already interpretable, like a decision tree, that can be a really good option too. Okay, let's talk about understanding how your machine learning models make decisions. Today we're diving into SHAP and LIME, two really helpful tools for that. Think of SHAP as using game theory to figure out which features had the biggest impact on a particular prediction. It tells you asterisk how much asterisk each feature influenced the outcome. Then there's LIME, which is like creating a mini model around a specific prediction to see what's driving it in that immediate area. They both help us move beyond just seeing yes or no and start understanding asterisk why asterisk a model made its decision really crucial for trust and debugging. Let's talk about bias in machine learning. It's a really important topic because models learn from the data they're fed, and if that data is biased, meaning it reflects existing inequalities in society, the model will likely pick up on those biases too. There are different types of bias that can creep in, like historical bias based on past prejudices, representation bias when certain groups aren't adequately represented in the training data, and measurement bias due to inaccurate ways we collect information about people. It's not always simple to figure out what fairness even means, so there are various fairness metrics we can use, things like equality of opportunity, statistical parity, and predictive rate parity, each looking at different aspects of how the model is performing across different groups. Okay, so let's talk about ethics in data science. It's a really important topic because the tools we use have a huge asterisk impact. Essentially, just because we asterisk and asterisk do something with data doesn't mean we asterisk should asterisk. We need to be aware of potential biases in our data that can lead to unfair outcomes for certain groups. Protecting people's privacy is also key, making sure their information is safe and used responsibly. And finally, let's try to understand how these models make decisions. Transparency matters. It's about building a future where data science is truly beneficial for everyone. Okay, let's talk about keeping your data safe when you're building machine learning models. It's super important that we don't just collect all the information available. Actually, minimizing what you collect is a great first step. That means only grabbing the data you truly need for your project. Next up, consider anonymizing or pseudonymizing any identifying details, basically replacing them with something else so they can't be traced back to individuals. Then, make sure your data storage and access are super secure, using encryption and strict controls. And don't forget about the models themselves, they can be vulnerable too. Finally, keep up to date on regulations like GDPR or CCPA. These rules protect people's information, and you need to follow them. Okay, let's talk about getting your machine learning models into the real world. It's not enough to just train a great model. You need to make sure it's consistently delivering results in production. That's where CI/CD comes in. Think of it like software development. You want an automated process for testing, building, and deploying your models. We're looking at key stages. First, data validation, automatically checking the quality of new data coming in. Then there's model training and evaluation, triggered whenever new data arrives or you need to update a model. Next up are tests and packaging, ensuring everything works together smoothly, often using tools like Docker. Finally, deployment automates getting your model online, and monitoring and retraining ensures it stays accurate over time. Okay, let's talk about keeping your data science work organized. First up is Git. It's a really powerful tool for tracking changes to your code and collaborating with others. Think of it like a super detailed version history. But what about those huge datasets? That's where DVC comes in. DVC essentially extends Git to handle big data, storing the actual data on cloud storage and linking back to your code. This means you don't need to commit massive files directly into your repository, saving space and making things way more efficient. Okay, let's talk about keeping track of everything when we're building machine learning models. It's easy to get overwhelmed with different experiments, versions of code, and all the numbers that come along with them. That's where data versioning comes in. Two popular tools for this are MLflow, and weights and biases, often shortened to W&B. MLflow is an open source platform designed to manage the entire machine learning lifecycle, from tracking your experiments to registering your trained models. It's really flexible and great if you want more control. On the other hand, Weights and Biases is a collaborative platform that offers a super intuitive interface for visualizing everything and making it easy for teams to work together. Essentially, both tools help us understand what's working, what isn't, and why, which leads to better models and faster development cycles. Think of them as your project management tool specifically tailored for machine learning. Okay, let's talk about API and RESTful services. They're super important for data scientists. Basically, an API is like a set of rules that allows different software programs to communicate with each other. Think of it as a waiter in a restaurant. Your code make a request, and the API delivers the information you need. RESTful services are a common way these API are built. They follow simple rules using things like HTTP requests, which you've probably heard of before. And understanding this is key because data often lies outside your own systems. You'll use them to pull in all sorts of useful information, from social media trends to connecting with other databases and building those awesome data pipelines. Okay, let's talk about the really important first step in any data science project: understanding the business. It's easy to get caught up in the technical stuff, but you need to start by figuring out why you're doing this in the first place. What is the organization trying to achieve? Who are they hoping to benefit? Then we need to think about what data is available and how it can actually help them reach those goals. Don't just build a cool model, make sure it delivers tangible value for the business. Okay, so let's talk about getting your data insights across effectively. The first thing is to really think about who you're talking to. A CEO will want a very different explanation than the marketing team, for instance. Visualizations are super important here. Charts and graphs can quickly show trends that would take pages of text to explain. But don't just present the data, tell a story around it. What happened? Why did it happen? And most importantly, what action should be taken based on those insights. Keep your language simple and focus on the recommendations you're making, because ultimately, great data is useless if no one acts on it. Okay, let's talk about storytelling with data. It's not enough to just crunch numbers. You need to present your findings in a way that people actually understand and care about. Basically, data by itself doesn't tell a story, it's up to us to craft one. Understanding why storytelling matters is crucial. It helps you connect with your audience, pinpoints the most important discoveries, and ultimately influences decisions. Think of a spreadsheet as just raw facts. Adding a narrative turns those facts into something actionable and memorable. Okay, let's talk about managing data science projects. They can be pretty tricky. First, you need a really clear understanding of what you're trying to achieve and why. Define the scope. What are you solving, and how will you know it's successful? Then, gather your data, make sure it's good quality, and assess if it's enough for your needs. Next, you'll transform that raw data into useful features and select the right model. It's not a one-and-done process. You need to evaluate the model and keep iterating until you get the best possible results. Finally, deploy the model and don't just let it sit there, monitor its performance. Tools like agile methodologies and project management platforms can really help keep things organized. Okay, let's talk about how data scientists need to think about privacy and security. It's not just a legal requirement, it's the right thing to do. We're going to cover the big ones: GDPR and HIPAA. GDPR mainly protects the rights of individuals in Europe, things like being able to see what data is out there, asking for changes, or having their information deleted. Then we have HIPAA, which is specific to healthcare in the United States and focuses on protecting sensitive patient health information. As a data scientist, you need to understand these regulations and how they impact your work. A good data governance framework helps with things like making sure your data is accurate, tracking where it comes from, and controlling who can access it. Okay, so let's talk about how the cloud is changing the game for data scientists. We're seeing a huge shift towards these cloud-native tools. Think of them as your supercharged data science platforms. Companies like AWS with SageMaker, Google with Vertex AI, and Microsoft Azure all offer powerful services. These aren't just faster, they're designed to scale up or down automatically based on your needs, making collaboration much easier for teams, and often offering more cost-effective pricing compared to traditional setups. Plus, you can access everything from almost anywhere. Okay, let's talk about AutoML. That's automated machine learning. Basically, it's like having an AI assistant help you build machine learning models. It takes care of lot of the tedious work involved, such as cleaning your data, figuring out which features are important, and even tuning the settings for different algorithms. There are several techniques at play here: automated feature engineering that finds the best way to represent your data, smart model selection that tries different algorithms to see what works best, and hyperparameter optimization that dials in those models perfectly. Tools like Google Cloud AutoML and Microsoft Azure Machine Learning Automated ML really make this accessible to a much wider audience, even if you're not a machine learning expert. Let's dive into graph analytics. It's all about looking at the relationships within your data. Instead of just focusing on individual values, we build a graph. Imagine nodes representing different things and lines connecting them to show how they relate. Techniques like centrality help us find the most important players in a network, while community detection helps us group similar entities together. It's incredibly useful across many fields, from spotting fraudulent transactions to improving recommendation systems and even understanding how drugs interact within the body. Let's talk about Bayesian networks. These are powerful tools for data scientists, and they really help us deal with uncertainty. Basically, a Bayesian network uses a diagram to show how different variables in our data relate to each other. Each box on the diagram represents a variable, like whether it's raining or if the sprinkler is on. Arrows show which variables influence all this. And then, we use something called a conditional probability table to tell us exactly how those relationships work. Okay, so let's talk about classification problems that are a little more complex than just picking the single best answer. We're moving into multi-class and multi-label scenarios. Multi-class is pretty straightforward, like identifying what animal is in an image. It can only be one thing: cat, dog, or bird. We use something called softmax to get probabilities for each class, and then pick the highest one. Now, multi-label classification is where things get interesting. Imagine a news article that covers both politics, and international affairs. That's multi-label. Instead of just assigning a single category, it can belong to several. We use models like binary logistic regression for this, predicting the probability of each label independently and then setting a threshold to determine which labels apply. Let's talk about survival analysis. It's a really powerful tool in data science when we need to understand how long things last. Think about tracking patient outcomes after treatment, or predicting the lifespan of a product. The key idea is that we're dealing with time to event data, events happening over time. A big challenge can be censoring, meaning we don't observe an event for everyone in our dataset because they might still be going strong when the study ends. We use concepts like a hazard function to understand the risk at any point, and then build a survival function that tells us how likely someone is to survive beyond a certain time. Kaplan-Meier and Cox proportional hazards are two common techniques we use in this field. Okay, let's talk about how quantitative finance and forecasting fit into the world of a data scientist. Essentially, you're using your analytical abilities to understand and predict what's going to happen in financial markets. This is where statistics really shines. You'll be diving deep into time series analysis, looking at historical data like stock prices or interest rates to see if you can spot patterns and build predictive models. Think about things like ARM or more advanced techniques. Then there's risk management, which involves building systems to protect against potential losses, a really important part of the job. And don't forget algorithmic trading. It's all about automating trading strategies using data. You'll need strong programming skills, especially with Python and R, along with solid SQL knowledge for getting your hands on the data you need. Alright, let's talk about how data scientists can really level up by working with images. Images are everywhere these days, from medical scans to photos on social media. But raw images, they're often a mess. That's where image processing comes in. We'll cover some key techniques. Noise reduction, basically smoothing out the picture to get rid of random fluctuations. Thresholding, turning black and white based on a specific value. Edge detection, highlighting borders and shapes. And color space conversion, changing how we see colors for easier analysis. These are just the basics. They are crucial stepping stones to more complex image-based insights. Let's talk about how computers actually understand what we say. Speech recognition is a really fascinating area, and it's becoming increasingly important for data scientists. Basically, the process boils down to 3 key steps. First, the system analyzes your speech and turns it into numerical representations like capturing the sound waves. Then, a language model comes in, figuring out how words fit together. It's like understanding grammar and sentence structure. Finally, a decoder uses both of these pieces of information to figure out what you are actually saying. Modern systems often use deep neural networks, which are incredibly accurate now. Okay, let's talk about how computer vision is becoming a really important area for data scientists. Basically, it's teaching computers to see to understand what they're looking at in images and videos. Think about self-driving cars needing to recognize pedestrians and traffic lights, or doctors using AI to spot anomalies in medical scans. Retailers use computer vision to track how customers move around a store. And manufacturers rely on it for quality control, spotting defects that humans might miss. The core of this is often building models using things like convolutional neural networks, powerful tools that allow computers to learn visual patterns. Okay, let's talk about something really exciting: edge AI and on-device machine learning. Basically, we're moving the brains of data processing from the cloud to the devices themselves. Think about your smartphone. It doesn't constantly send all its data to a server for analysis. Instead, some of that happens right there locally. It's achieved by using smaller, more efficient models, leveraging hardware like NPU in our phones and wearables, and often doing some initial data work on the device itself. The result? Faster responses, better privacy because less data is transmitted, and reduced costs for bandwidth. Okay, let's talk about federated learning. It's a really exciting concept in data science that addresses the growing need for privacy when training AI models. Basically, instead of bringing all your data to one central location like a big server, we train the model directly on each device where the data lives. Each phone, for example, trains its own little version of the model using only its users' information. Then, only these changes or updates are sent back to a central hub, not the actual data itself. The server combines all those updates and builds a better global model. It's like a team effort where everyone contributes their knowledge but keeps their secrets safe. Okay, let's talk about how we're using some really powerful tools to tackle natural language processing problems now. Instead of building models from the ground up for every single task, which takes a lot of time and data, we use a technique called transfer learning. Think of it like this. You've already learned basic grammar and reading skills, so when you start learning a new subject, you don't have to learn everything from scratch. It's the same with these models. We take pre-trained models like BERT, GPT, and T5, which have been trained on massive amounts of text, and adapt them for our specific needs. BERT's really good at understanding what's already in a piece of text, GPT is fantastic at generating new content, and T5 handles pretty much everything as a text-to-text problem, making it incredibly versatile. Each one has its strengths depending on what we're trying to achieve. Let's talk about data augmentation. It's like giving your model a little extra training material without actually collecting more raw data. When you have limited information, it's a fantastic way to boost performance and make your models more resilient, essentially teaching them to recognize patterns even with some variations in the input. Let's talk about synthetic data. Essentially, it's fake data designed to look and act just like real data. It's a huge tool in the data scientist's toolbox because it allows us to overcome some really common challenges. When real data is hard to get, maybe it's private or too difficult to collect, synthetic data steps in to fill the gap. It can also help when we want to make sure our models aren't learning biases from limited datasets, and it's fantastic for testing out new algorithms without needing a massive amount of real-world information. Okay, let's talk about 2 exciting techniques that are changing how we tackle data science problems: semi-supervised and self-supervised learning. When you don't have tons of perfectly labeled data, which is pretty common in the real world, these approaches can be a huge advantage. Semi-supervised learning takes what we do have, which might be a small amount of labeled data mixed with a much larger pool of unlabeled data, and uses that combination to train better models. Think of it like having a little bit of guidance alongside a lot of observation. Then there's self-supervised learning. This one's even cooler. Instead of relying on labels at all, the model figures out how to create its own fake labels by predicting parts of the data from other parts. It's like teaching itself what's important just by looking closely at the data. Okay, let's talk about making our models more efficient. We want to reduce their size so they run faster and take up less space. That's key for deploying them in real-world applications. One really important technique is called quantization. Basically, we can lower the precision of the numbers used inside our model. Think of it like rounding things down a bit. Then there's pruning, which is like trimming away unnecessary connections in the network. It's not about removing knowledge, but making the model more streamlined. We also have knowledge distillation, where a smaller student model learns from a larger, more complex teacher. Finally, low-rank approximation, or low-raw, is a clever trick for reducing the number of parameters by cleverly breaking down matrices. The best method to use depends on what kind of model you're working with and where you plan to deploy it. Okay, so let's talk about how we can really learn data science effectively. Instead of just reading textbooks or watching lectures, which is great for the basics, it's hugely beneficial to actively engage with the subject. Think of active learning as taking control of your learning journey. We're not passively absorbing information, we're constantly testing our understanding through things like real-world case studies, where you get to tackle actual datasets and figure out what's going on. Coding challenges are also key. They help build those crucial programming skills. And don't underestimate the power of building your own projects. Even a simple project can solidify your knowledge. Finally, explaining your work to someone who isn't familiar with data science forces you to really understand why you made certain decisions. Okay, let's talk about the core tools data scientists use specifically, some really popular open source machine learning frameworks. First up is scikit-learn. It's a fantastic starting point, especially if you're working with traditional methods like regression or classification on unstructured data. Then we have TensorFlow, developed by Google. It's a giant when it comes to deep learning and can handle massive datasets and incredibly complex models. PyTorch is another big one, created by Facebook, and it's particularly favored in the research community because of its dynamic graph, making it super flexible for experimenting. Finally, there's Keras. It simplifies building neural networks, whether you're using TensorFlow behind the scenes or not. It's all about getting your models up and running quickly. Okay, so let's tackle these terms. Artificial intelligence is the overall goal, getting machines to be smart like us. Machine learning then gives computers a way to learn from data without needing specific instructions for every single scenario. And deep learning? That's just a more powerful form of machine learning that uses really complex networks to handle incredibly complicated problems, like understanding images or speech. Okay, let's talk about how data scientists are using AI to revolutionize various industries. We're seeing some really exciting developments. In healthcare, AI can predict illnesses before they even develop, leading to much faster and more targeted treatment. Manufacturers use it for predictive maintenance. Basically, the machines tell them when they need fixing before they break down. Retailers are personalizing recommendations like never before, keeping customers engaged. Finance uses AI to spot fraudulent activity in real time. And of course, we can't forget about transportation and autonomous vehicles. That's a huge area of growth. It really highlights how data science is driving innovation across the board. Okay, let's talk about building data products. It's not just about fancy algorithms, it's a structured process. We start with clearly defining the problem, what are we trying to solve and who benefits. Then, we gather the necessary data, checking its quality along the way. Next comes prepping that data, cleaning it up, transforming it, and creating new features. After that, we build and evaluate our machine learning models. Finally, we deploy them into a real-world setting, keeping an eye on how they're performing and retraining as needed to make sure they stay accurate. Okay, let's talk about a common hurdle in data science: class imbalance. It basically means one category, like maybe fraud detection or rare diseases, has far fewer examples than another. This can really throw off your models because they'll naturally be biased towards the more frequent class. It's important to understand why it matters, as models trained on imbalanced datasets often perform poorly when trying to identify those rare but sometimes critical cases. Luckily, there are several strategies we can use. We can resample the data either by increasing the number of samples in the minority class with oversampling techniques like SMART, or reducing the number of samples in the majority class through undersampling. Another approach is to use cost-sensitive learning, where our models get penalized for misclassifying the minority class. And finally, we have ensemble methods specifically designed to handle this imbalance effectively. Let's talk about how we tackle imbalanced datasets in machine learning. It's a really common problem. Often, you'll have one class that's way more prevalent than another, like detecting fraud where fraudulent transactions are rare. This can cause your models to be biased and perform poorly on the less frequent but crucial class. Oversampling is a technique we use to fix this, and SMART is a fantastic method within it. SMART doesn't just duplicate existing data. Instead, it cleverly creates new synthetic examples of the minority class by looking at its neighbors and blending them together. It's like saying, okay, let's build similar but slightly different instances based on what we already know. This helps your model learn better about that minority class, leading to more balanced and reliable predictions. Okay, let's talk about ROC curves. They're a really useful way to visualize how well your binary classification model is doing. Basically, they plot two things: the true positive rate, that's how many of the actual positive cases you correctly identify, against the false positive rate, which tells us how often we incorrectly label negative cases as positive. The area under this curve, called the AUC, gives you a single number to tell you just how good your model is at telling these things apart. A higher AUC means it's doing a better job of distinguishing between the classes. Okay, let's talk about precision and recall. They're key concepts for data scientists. Essentially, precision tells us how accurate our positive predictions are, while recall measures how well we find all the actual positives. Often, there's a trade-off. If you want to catch everything that might be a problem, high recall, you risk making a lot of mistakes and incorrectly identifying things as problems, low precision. Conversely, if you prioritize minimizing false alarms, high precision, you might miss some real cases, low recall. It's about balancing these two metrics based on the specific needs of your project. In spam detection, we want to be really careful not to mark important emails as spam, and in disease diagnosis, we need to make sure we catch as many actual patients as possible. Do you want me to elaborate further? Okay, let's talk about bias and variance. They're really important concepts for any data scientist. Think of it like this: bias is how far off your model's predictions are from the actual answers it's consistently missing in one direction. High bias means our model is too simple and can't capture the underlying patterns. Then there's variance, which measures how much your model's predictions change when you feed it slightly different training data. A high variance indicates that it has learned the noise in the data instead of the signal. It's basically overfitting. The challenge is finding the right balance, a model with just enough complexity to avoid both bias and excessive variance, leading to good predictive performance. Okay, let's talk about a really common challenge in building great recommendation systems: the cold start problem. Basically, when you have brand new users or brand new items, it's super hard for your system to know what they might like. We call this a cold start. There are three main types. You could be starting with a completely new user who's never interacted before, or you've just added a new product that nobody has rated yet. And sometimes, when you launch an entirely fresh recommender system, you're facing all of these at once. So how do we tackle this? Well, one approach is to use content-based filtering, figuring out what items are similar to things a user *** liked before and recommending those. Another simple option is just suggesting the most popular items, which can work well as a starting point. Finally, you can combine these techniques in a hybrid approach for more tailored results. Okay, let's dive into anomaly detection in time series data. This is super important for any data scientist because it helps us spot things that are out of the ordinary. Think about monitoring server performance or stock prices. These can be tricky to analyze without flagging unusual events. We'll cover some common techniques, from simple statistical methods like moving averages to more complex machine learning approaches like isolation forests and even deep learning with LSTMs. For example, a sudden spike in server CPU usage followed by a drop could signal downtime, a critical issue to address. Okay, let's talk about making our data science projects handle big asterisk data. As we work with more and more information, simply throwing more power at a single computer won't always solve the problem. We need to think about scalability. How can we make our workflows grow along with the data? One really important technique is distributed computing, where we break down the processing across multiple machines. Cloud services are also huge. They let us easily adjust resources as needed. And don't forget database optimization, making sure we're getting the most out of our data storage. Finally, a microservices approach can help to keep everything manageable and scalable. Okay, let's talk about dashboards. As data scientists, we often get caught up in the technical details of our models and analyses. But it's crucial to remember that our job isn't just to build amazing algorithms, it's to communicate those insights effectively to business users. Dashboards are key for doing that. The first step is really understanding who you're building the dashboard for, what questions they need answered, and which metrics truly matter to them. Then, we need to carefully choose the right visualizations. Think about how best to represent the data and tell a clear story. Keep it simple, focus on the key insights, and don't be afraid to add some interactivity so users can explore the data themselves. And most importantly, always get feedback from your stakeholders. Dashboards are living things that need to evolve as business needs change. Okay, let's talk about streamlining your data science workflow, automating it. Why is this so important? Well, manually doing everything from gathering your data to building models takes ton of time and can be really error-prone. Automation helps us avoid those mistakes, speeds things up dramatically, and lets our data scientists focus on the truly creative parts of their job. We'll look at some key strategies, like automating how we get our data ETL, how we train models, and even how we generate reports, so it happens consistently and efficiently. Let's talk about building trust in your work as a data scientist. Reproducible research is absolutely key. It's all about making sure that anyone can understand, verify, and repeat your analysis. We start with version control like Git, which lets you track every change you make to your code and analyses. Then, managing your environments with tools like Conda or Virtualenv ensures that the exact same libraries and versions are used across different projects. Clear documentation is critical too. Don't just present the final answer, explain how you got there. And finally, good data management practices, including tracking where your data comes from and making sure it's clean and consistent, are essential. By focusing on these steps, you build a strong foundation for reliable insights and credible results. Okay, let's talk about making your data science code really shine and easier to work on for everyone else. We need coding standards and best practices. Why? Because consistency is absolutely vital. It makes it a whole lot simpler to read, understand, and maintain your projects. So, there are some key principles like DIY. Don't repeat yourself, just keep it simple, stupid, and Yagni. You aren't gonna need it. It really helps when you follow these guidelines. Also, adopting a code style guide like PEP8 for Python is super helpful. Lintus can automatically check your code to make sure it meets the standards. And don't forget version control with git commit often and write clear messages, plus use branching strategies. Thank you for watching.